Hey everyone, this is Pry here, and this is sort of just it's kind of a test. Um, so I've been meaning to make some videos on CS papers that I like to read, as well as just sort of general systems programming like things, particularly operating systems and stuff. But I just wanted to quickly go over, I think, a question that is useful and I think will uh, sort of make more clear what I'm trying to do, I guess. And the question is what is a computer? Uh, and I guess what I'm trying to get at is like what is a computer, aka why do programmers need to know about hardware? Um, and so what is a computer? I think the like a one correct answer would be it is an abstraction. It is uh, something that, at least to the programmer's knowledge, is a simplified view of something that is pretty complicated. I guess an example of an abstraction would be, I don't know, say we have three circles. Our abstraction of this could be some uh, Arabic numeral, perhaps. Um, uh, we get rid of the detail that these are circles or whatever, and we instead now have a abstracted view. Um, Alfred Aho, one of the a pretty famous computer scientist, has said that computer science is a science of abstraction, and so many of these things are. So, what does the programmer's view of a computer really look like? Um, so, this is kind of our model of computation, if you will. We've got the CPU here. I've drawn it as like a sort of little pocket calculator, and this by itself can't do too much. It needs to be connected to some memory. This is a large bank of memory, whether it's RAM or disks or notebooks or whatever. And this by itself is not super useful uh, unless you can actually get at what it's calculating, right? And so we need some form of communication to the outside world, um, whether this be monitors, keyboards, displays, typewriters. Typewriters were one of the first, punch cards, even the network, like a network card and so on. Um, and so this is kind of what the computer looks like to a programmer. These are like the main parts. Um, but uh, and just sort of to, I guess, describe these parts more. The CPU uh, is a calculator. It can do basic calculations, but it can also understand a program. This program is typically stored within the memory. It's just a list of things to do. This gets piped into the CPU. The CPU does them one at a time. Um, and what's important to note is that that's what the programmers, think. Um, the computer should look like it goes one instruction at a time. The important thing to know is that pretty much any CPU, at least in say your phone or say your laptop or anything, none of them actually sequentially go through instructions. They will do what's sort of known as like a superscalar architecture, and they'll be running multiple instructions all at once, and only at the very end of the sort of execution, they'll sort of make sure that the state looks like it's been executing one at a time, when in reality, 4, 5 instructions or whatever can be executing in parallel. Same with memory. Memory, at least to the programmer, looks like a linear array of bytes. It's just a list, and we can address into it, and that's kind of what we're at least taught. But what's important to know is that memory is far more complex than that. In fact, I think memory can be thought of as almost a root of all evil in systems programming. So much work goes into making sure that memory is actually efficient. Um, and IO, I don't have too much to add there. So here's kind of the view of some abstractions. We've got the software, we've got the hardware, And here is a sort of contract, if you will, between the hardware and the software, the assembly language. So the assembly language is the binaries, the sort of bits, if you will, that are able to be understood by the CPU. The CPU says, okay, this set of bytes means add, or means do some branch, or do whatever. These are the instructions that the hardware understands. And the software essentially is written in these instructions. The issue is that, as with pretty much any non-trivial abstraction, it's a leaky abstraction. There's essentially ways in which the hardware you get to see the complexities of the hardware when in reality the hardware is trying to make it make sure that you don't, or try to keep the programmer's view alive. The best example of this is say we've got some array here. It's a long array. It's going off the page. One example is, say we're iterating over this array. We're going, okay, I'm looking at this element, then I'm looking at the next one, and so on and so forth. This is extremely fast to do. Now say I start somewhere random, and I go somewhere random, and I keep doing this sort of randomly, and I go through every element, but randomly instead. This is like probably orders of magnitude worse, since when we're doing just a simple linear iteration, the memory subsystem of the computer actually will sort of assume, hey, this person is iterating over a list, or it doesn't even need to assume that. Essentially, it thinks, okay, it's accessing some point of memory. Let's bring in a bunch of other memory surrounding it. Memory that stays together is often used together. That's sort of the principle that the computer is using. And when linearly iterating over an array, which is an extremely common thing, this is correct. When you're doing something random, even though you're technically doing the same logical thing, where we're going over this thing, if as long as order doesn't matter, this is much more expensive, since the prefetcher in the CPU and the memory system is not really able to efficiently page in stuff into the cache. So this is kind of what memory will look like. We've got registers here, registers and the L1 cache. These are within the CPU. DRAM is next, and then there's SSDs and hard disks. And what's being shown by this hierarchy of memory is that the things at the top are extremely fast. They're also extremely expensive. We cannot possibly make all of our computers using the technology, all of our memory using the technology that CPU registers are made on, because it's just too expensive to do so. Similarly, registers in these caches, the caches are also pretty expensive, and so we've got these different caches. DRAM is less expensive and it's larger. And then there's also one very interesting barrier here between the RAM and the hard disk, or the SSD, which is that everything up here is volatile, meaning that essentially the sort of circuits they're using to store bits have to be constantly refreshed. When you're sitting in front of your laptop and you're doing nothing, RAM is constantly being refreshed over and over and over again. Essentially, your RAM is writing to itself, writing the whole contents of it many times per second. While in something like NAND flash SSD or hard disks, that is not the case. You can disconnect it from power and the bits are generally fine. And this is sort of the memory that is the cheapest. The other thing to note is that registers are super fast. L1 cache is a little less fast. DRAM is 10 times slower. And then hard disks and SSDs are really, really slow, at least relatively. We're still talking on the order of nanoseconds or milliseconds, but when doing something on the registers is like nanoseconds, like negligible, DRAM might be orders of magnitude greater, and hard disks similarly. So it's very important to know. But the thing that I wanted to point out, especially with assembly languages, is that assembly languages typically only kind of have two main ways of this isn't generally true, but like typically we'll have two main ways of thinking about memory, which is you could either load some part of memory, say, hey, computer, give me whatever byte or whatever word. Word is just a collection of bytes that's like the size, that's like the native size of your processor. So like 64-bit processors uh, will have 8-byte words, if I'm getting that correct, and 32-bit will have 4-byte words, and so on. And so let's say, hey, load me this word or load me this byte. It'll get this from memory, and store is, hey, take this thing, usually something in the registers, and store it within the memory. This is kind of all programmers can do with memory. Um, Depending on your assembly language, there's more complex things, but these are the general interfaces to actually communicate with the memory. The issue is that you notice if, to the programmer, and this is kind of a good thing, this is entirely transparent. This whole hierarchy is something that you don't see really, um, which makes it really easy to program for. Um, I never have to think about, hey, am I getting something in memory from DRAM, or am I getting it from L1 cache? That's just not a problem that I have. Uh, but this means that uh, there's a lot of work being done to try and make this efficient. Lots of cache coherence protocols, lots of memory exchanging hands, and so on, um, all without the programmer really knowing. Um, and so um, this is sort of, I guess, my whole argument is that systems level programmers, the type of stuff that I hope to be talking about, um, we always really need to be mindful of at least kind of how the hardware looks. It's really important since uh, so many design decisions and even just so many programming decisions uh, have to be made with things like the hierarchy of memory and superscalar processors in mind. Um, yeah, hopefully that was fun, or at least informative. I'm testing out this whole setup. Let me know if you have any comments, suggestions, and next time I will either start the operating system series or review one of my one of the papers that I enjoy. So, thank you.